John is the Executive Director of Vice President of Science Commons, and John is going to, we made him do double duty. He's not only going to give us his fascinating presentation on science, but he's also going to chair this workshop for us, or this panel for us.
Yes, to introduce myself, I'm John. My bio's in the packet, so I won't go into it. It's never fun following Jamie, which is why I have slides, and he doesn't. So I was asked to talk about a semantic web for science, and I'm going to try to explain what that means as I go forward. But I like to start with a couple of questions, because it's easy to forget this as we get going. And the first question I want to ask is, why is access so important that we want to have a conversation about copyrights, limitations, and exceptions? But I also want to talk about why the way we achieve that access is so important. Because there are a lot of different ways to achieve access. And we can talk about the way the NIH has been achieving access through the PubMed Central mandate, and we can talk about price barriers and permission barriers. But I want to try to answer both of these questions. So as Jamie said, I work at Science Commons, and so our focus is more on human health. And this is why access is important to me. This is the black fly. It's the carrier for a disease called river blindness. It affects about 18 million people in the world. It's the #2 leading cause of blindness in the world. And there is a drug for it, but you have to take it for 15 years every day, and it doesn't actually kill the worm that causes river blindness. So there's no market for this disease. It's a devastating disease. 18 million people have it. If 18 million people had it in the US or the EU, there'd be 3 biotech companies competing to cure the disease. But we don't have that. And that's because it takes about $1 billion in 17 years. You can argue about the numbers, but it's a long time and a lot of money to go from what we know about the body or a disease to a drug. And that's because, not that people are evil, but because not only do we not have a good cure, we actually can't even afford to look. Because no one can risk $1 billion with no promise of return coming back. And there's a lot of arguments about prize models and different funding models and all of these different things about how to deal with this problem. But the fundamental problem is a knowledge gap, which is that we don't know how to deliver drugs to cells. We don't know how to meaningfully understand how diseases work. We don't even know how Tylenol works. And it's been on the market for 50 years. We don't know very much at all. There's a knowledge gap. And so I thought I would be ironic and use a Gates quote on a day about sharing and limitations. But Gates actually gave a beautiful speech at Harvard last year where he talked about the barrier to change is not people not caring enough, it's complexity. And in particular, you need to be able to see a problem, see a solution, and see the impact. And complexity blocks all 3 steps. And so part of what I'm going to argue is that access provides us with the methods to defeat complexity by letting lots and lots of different people attack different pieces of the problem and have their contributions come together. Access is actually one of the only non-miraculous tools we have to defeat complexity. So the process by which we manage complexity in science is something that we call the research cycle, scientific method. There are a lot of different ways to talk about it. And roughly speaking, you search, you read, you discover tools, you order the tools, you run experiments, and then you republish. And this regenerates the knowledge space in science. But there are blockages at each of these points. Some of them are legal, some of them are social, some of them are technical, some of them are institutional. And what we're going to focus on today is the impact of the publish, search, read part of the cycle. But because this is a cycle, blockages in the tool discovery, ordering, and experiment also create problems. And so as we try to solve the access problem, the way in which we solve it dictates whether or not we simply move the problem to a different part of the cycle. So not only is access important because it lets lots of people solve big, complex problems. Think of the way that Wikipedia lets lots and lots of people working individually create a very complex knowledge organism. But the commons as a methodology, something that's contractually constructed, that's built on the public domain, that tilts towards sharing, that uses technology well, that as a methodology for access is actually much more efficient than simply saying put your PDFs on the web. And if you don't think about the copyright usage aspects of this at the very base, you have a very significant chance of not actually releasing all of these barriers. So one argument is that information flow drives the processes by which we manage complexity in science, And access lets us exploit the technologies and actually change those processes in a way that's innovative. So this is going to be a gross simplification. But we can talk about two different network-driven process revolutions. One is the mixture of computers, networks, and technology standards, which said, here are standards by which we move bits between each other, and that gave us the internet. Now, if you read the proto-histories of the net, the reason the net was created was because a guy at DARPA was angry that he had 3 computers that couldn't communicate with each other. And they had a lot of choices as to how they would solve that problem. But they chose to solve it in a very simple manner that was open and said any computer that wants to join adopts the standard. And that's where the internet came from. And because it was an open standard, 20 years later, Tim Berners-Lee could come along and say, well, I want to network documents, not just computers. And that's where we get the World Wide Web. It was not foreseen by the creators of the internet, but the choice to allow access to the network in a way that didn't discriminate documents or protocols allowed an unforeseen use to be created. And then, in turn, Tim Berners-Lee did many of the same things. He said, I don't care what you link on the web. And that let us get things like Amazon and eBay and Google, which Tim never really envisioned. And so when I talk about the methodology for access, what I want is the methodology process of what I call the research web or the knowledge web. And this is when we're trying to do for knowledge and ideas the same thing that we've done for computers and for documents. But the difference is no one was paying attention when the internet was created or the web was created. But there's already a very significant control culture and economic culture around the knowledge that we're trying to network, especially in the life sciences. So with that, I'll dive into the heart of it. So I like to show, it actually doesn't render very well on this. It's a hand holding a sheet of A4 paper. And the fact that we even call these things papers indicates where our brains are to this point. So we've spent hundreds of years thinking about these things as papers, thinking about knowledge as something that we compress down to a flat plane and communicate in words. And that's been a limitation of the technology of paper. But we don't have that limitation anymore. But as Jamie has beaten into me, the very act of fixing the knowledge in a tangible medium means that we get a copyright on it. And this may be very useful for music or for photographs or for songs and creative works. But for scientific works, this is the kind of sentence that is communicated in the life sciences. It's not very creative. You could argue that the more creative that the grace and the styling of this sentence acquires, the more creativity it acquires, the less scientifically valid it becomes. You know, and this is the way we think of it as a paper. It's just a sentence. It's something that we read. But this is how a lot of things look on the web, and they are networked knowledge. And so each of these entities in here has an identity on the web someplace other than this article. And it is not linked in any of the paper that we get. So this is just one sentence. And we can zoom out a little bit and say, well, what about an abstract? So I chose this one sort of at random. And then I went through by hand and checked all the different places where there should be hyperlinks. And there are none. And so you can extrapolate, again, from the sentence to the abstract to the full text. And you can start to imagine all of the things in scientific papers that need to have hyperlinks to other things. But because we think of them as papers and not as networked knowledge documents, those links don't exist. And that does things that that create significant other problems. It means that Google doesn't work because Google analyzes the links between things. And the only links between papers we have are citations, which even those, for the most part, are not hyperlinked. And that leads us to this problem, which is the way to deal with information in the life sciences is to do a keyword search. So here is a typical protein. If you've ever seen me talk, I always use this one because it has such a great number. 45,554 papers about this one. That's a lot. It's well over 100 years if you're going to read a paper a day and no new papers are published. So that's probably not a satisfactory solution. 17,000 of them are available in full text, which is actually a remarkable improvement. When I started using this 2 years ago, it was about 10%, and now it's up around 35%. You also see 9,600 core gene sequences, 6,400 protein sequences, 350,000 data sets, and the screen cuts off So there's a lot of information that we've created, but the only way to get at it is through, again, this human interface. But it's essentially, it's like having a dust storm of information. You don't know what's valuable in all of this. So maybe you go to Google and you search for P53. Well, that's actually even worse. There's 6,570,000 results, and none of them are really papers. Anyone who knows anything about P53 will find nothing new here. What the heck? Why is my computer talking? It doesn't usually do that. So this is from a CEO of a semantic web company, and it's about sort of the limits of keyword search. And what you see here is a graph that's showing that the utility of keywords as you get more and more information really goes down. Because if you have more and more information and more linkages, keywords bring you back less and less relevant information. The only thing that makes Google able to work is that it analyzes all the connections that we make as a way to judge relevance. And so what you see is that as we move up, we need to have far more structure to the information. Tagging is one way to think about it. More natural language in which you don't simply look for documents containing John Wilbanks, but documents that make some assertion about me, my creditworthiness, my speaking, whatever. But ideally, we get up to the point where the computers can make basic inferences for us. And this is very important in the sciences because what you really need to do in the sciences in one of the buildings right around the corner from here is go from A to B to C to D to E. And to be able to make those jumps as much as possible based on everything that's known about each of the steps. But right now, even though we might know A causes B and B causes C and C causes D, it's extremely unlikely that a scientist can rapidly use the information to evaluate all of the hypotheses he or she has. And so something's got to give. And the question is, what's it going to be? Are we going to essentially bet on or expect another monopoly like Google or Microsoft? Or are we going to try to build an open system where we have lots of competition on searching the knowledge space as opposed to one company that controls the knowledge base because they got there first? So one way I like to think about it is analog drafting versus CAD/CAM, computer-aided design. We don't expect modern building engineers and civil engineers to use ancient tools for drafting. But from a technical perspective, we're asking life scientists to use ancient tools. Basically pre-Google, mid-90s level of search. And that is primarily driven by the lack of access to the literature. So here's what it could look like. And this is the unfortunately named IHOP, which is a pancake house chain in the United States, if you don't know. But it means information hyperlinked over proteins. And so here's the same protein. It's P53. We have all of the synonyms for it, which is a wonderful resource for machines, because it means that one query to just this name gets all of the information for all of these names. And we have all of these great sentences about P53 that you can read without having to find them in the paper. This is the key functional information. Now, what's really cool is you can click on these beakers on the right and actually get the data sets that establish these facts. And you can click on these and build a little graph model of relationships among genes and see all of the sentences that establish that graph model. Now, this is a modern way of interacting with the biological literature. But it can only run on the abstracts because, for the most part, it's illegal to do this on the full text of the software. And if you think about an abstract versus a paper, I'm sure most of us here have written papers. Abstracts don't usually have everything in them. And in particular, in the life sciences, references to the materials, the methods, and the data are buried in the full text. So going back to that research cycle, if we don't think about the full text, we can't even begin to link the materials to where you might order them on the web, or the data sets to where you might access them on the web. And just to don't think I'm lying, here is the contract Elsevier uses to make this illegal. This is the one they signed with the University of California Digital Libraries. It's on the California Digital Libraries website. They actually have all of their contracts published. There's a link in my paper, which is in here, if you ever want to do research on it. And the exact words are, subscribers shall not use spider or web crawling or other automated software programs, routines, or robots to search and index. It's illegal. So PubMed Central, again, the way we get access, PubMed Central has about 1 million articles. Permissions are granted on about 50,000 of those articles, which means that 6% of the full text is actually available for legal text mining. The rest have price barriers removed, not permission. And that represents 0.003 of PubMed. So this is from the director of libraries at Biogen IDAC, who I interviewed yesterday for our website. And this is his quote. And I won't read it to you. But you can sort of see that the abuse of pharma is in many ways misguided because they make money if they treat disease. They're not sitting around trying to not cure people. But in many cases, they are themselves overwhelmed by the complexity of the knowledge space and their own internal organizational complexity. And the literature is actually the touchstone to which all pieces of the company refer. But even Biogen can't rationalize the licenses. So the quick promotion is that, of course, an answer to this is open access, Creative Commons, where I work. We have over 500 journals under CC BY, the most liberal license we offer. That's about 15% of the global total. We hope that number increases. But the literature is just a piece of the knowledge space. So if you think about the literature in the context of databases, here's a visual representation of the minimum set of databases you need to answer an interesting question about brain disease. So this ties in, and again, the way we solve the access problem in literature needs to be different than the way we solve it in data, because otherwise we're going to keep promulgating problems in the research process. So rationalizing those database licenses is nearly impossible. This is the molecular biology database collection. It goes up to 970 databases. And that's just molecular biology. I've had two very smart lawyers for free trying to analyze all the licenses on these. They've made it through 50 in a month. Because finding the licenses is hard, and then understanding them is harder. And in the absence of a clear declaration, you have to assume that there's control. So what you see is when you integrate all of these knowledge bases, it's like the inverse of the GPL. The most controlling license propagates, not the least controlling license. This is a very difficult point in many cases. It was hard for us to accept. It took us 18 months to accept that the most restrictive license had to apply to any integration of databases. And so we've put together a protocol on this, which basically says, don't assert your rights, converge on the public domain. And we'll go into all of this stuff later. I'm putting this mainly in tabs so you have it in the slides. And so we've actually done this at Science Commons. We've gone out and aggregated these databases. We've negotiated the rights to do this aggregation. Because we have lawyers and technologists, we can afford to do it. But what we're trying to do is to give this away under the theory that people will now figure out their terms and put their database into it because they would like their data to be visible. The same reason that Google has forced some access to come about. So the reason for this is that read 189,000 papers is not the right answer for scientists to deal with the knowledge space. This is a query we got from an Alzheimer's group, which basically said, give us a list of genes that might be good drug targets for Alzheimer's disease. And Google is the state of the art, throws back 190,000 scholarly papers. And what you want is to get better answers through integrated data. So this hideous thing over here is query code for the semantic web that queries that integrated knowledge base. And what we do is we start with a public government information resource, which is a taxonomy of things, using one word for pyramidal neurons, a kind of brain cell. We've got a mapping of the journal articles associated with that. There's a mapping provided by the government in another place that has the genes mapped to the papers. We extract that. And then we filter it by yet another US government resource, which basically categorizes those genes. 4 public information sources available in 4 different places related to each other, unintegrated, unintegratable by anyone but an expert. And that's basically what we've done to ourselves is hired the experts to do this, but to give it away. And what you get is actually a list of genes instead of 190,000 papers. It's not complete, it's not perfect, but it's a much better parsing of the knowledge space than the alternative. Now the rub is that this is probably a prohibited query if any of the databases have copyleft or non-commercial licensing or database derivative licensing or anything like that. Because we don't know what a derivative work is. We don't know what a transformative use is. We don't know what attribution means or non-commercial or copyleft in the context of databases. This is only possible because we restricted ourselves to databases in the public domain. What's really cool is you can render that entire query as a web link, so you only have to look at the ugly thing once, and the next person runs it like this. So this is the sort of ability to manage the complexity through a mixture of technology and access. Because access means I can come along, you know, my science geeks can write the first one, but I can come along and just change the terms using an automated button on a website, and I can actually do permutation and recombination on that query and get a second query in less than 30 seconds. So again, all of us can begin to combat complexity if we have enough access to use the right technologies. And so the information itself becomes a part of the ICT infrastructure. And we have to start thinking about those same dumb network end-to-end principles. So the core argument about why we need access and why we need to do access in a commons is that if we do the collaborative stuff based on good technical design and good legal design, all of us can begin to have processes that can attack complexity. So that's what I mean by the semantic web for science. And I'm going to end with a little thing I like to talk about. So we've been talking about the sciences that we want to develop. But sort of there's an irony about all of this, which is that the stuff that we don't expect tends to be the most innovative. Otherwise, we could predict innovation much more efficiently. So all of the money that went into turning the genome into A's, T's, C's, and G's has had a very significant dividend that we never expected. It's made the cost of sequencing and synthesis of DNA very low. And it's like the peace dividend in war, but I call it the genome dividend. So I went on last night at my hotel. This is what it costs to buy a DNA sequencer on eBay. Now you can get them for less, but they're not verified, and they won't ship worldwide. But this one, they take PayPal, and for $180 on top of this, 6 months no payment offered, you can have a DNA sequencer in your garage. And that's the write, right? That'll take the DNA and write the A's, T's, C's, and G's for it. Sorry, it's the read DNA. It'll let you basically read the DNA and get digital stuff. For 66 cents a base pair at MrGene.com, you can have the DNA written. And the cost of this, again, 2 years ago, this was $3 a letter. It's dropping rapidly. And the economies of scale that we had on digital optical media are coming to DNA. And so, you know, access is important because we want to take care of ourselves and be human and comprehend the complexity that we've got. And the way that we get it is important because we want people to not have river blindness and we want our children to live meaningful lives. But if we can't deal with the stuff that we're doing on purpose, which is what we're doing now, with the systems that we have, and access can help us deal with that, then access, again, it's one of the only non-miraculous tools we have to deal with the complexity that's coming. And just to finish, this is the Discovery Channel's DNA Explorer Kit. It's for ages 10 and up. It's $80. We have one in the office. And it's an honest-to-God DNA gel electrophoresis chamber. So this stuff is coming much faster than we can possibly expect. And the only way we're going to deal with the impact of teenagers writing code in DNA is to have enough access to understand what they're doing as soon as possible. And if we don't put these systems together, this is going to make the digital revolution, you know, look pretty mellow. So with that, I'll stop. Here's how to find me.
Fear of teenagers, John. This is a new meme. I haven't heard that.
Thank you. Thank you.